So here we have Olaf is made up of 21,000 centimeters cubed. How many feet cubed is this? So it's metric to English, my bad. So we have this many centimeters cubed. How many feet cubed is Olaf? And it gives us 1 inch is 2.54 centimeters. So in order to calculate how many feet cubed Olaf is, we're starting with centimeters cubed. And then since our metric to English is centimeters to inches, the first thing we need to do is go from centimeters cubed to inches cubed. And then we can go to feet cubed. So the only other additional conversion factor we need is how many feet in an inch, and ultimately how many inches cubed in a foot cubed. So we all know that there's 12 inches in 1 foot. We also have 1 inch, 2.54 centimeters. So the first thing we need to do is cube those conversion factors. Again, we have to cube them because we're dealing with cubed units. We need to cube the conversion factors before we start doing our calculations. So again, if you don't have the cube function, you just can go 12 times 12 times 12. It'll tell you the cube value of 12 cubed. So now we have the cubed conversion factors. Now we can set up our dimensional analysis. So again, we're starting with centimeters cubed. Now the first step, we want to convert centimeters cubed to inches cubed. So in our conversion factor of centimeters cubed to inches cubed, centimeters cubed goes on the bottom and inch cubed goes on top. So now we have inches cubed. The next step is feet cubed. So again, since we're starting with inches cubed on the top to the left, we need to put inches cubed on the bottom and feet cubed on top. So now you'll notice everything cancels but feet cubed. So again, you multiply everything on top, divide by what's on the bottom. The calculator tells us that many feet cubed. Let me double check my work. So that's the answer, but we need to do significant figures. So we take a look, our initial number, 21,000, has two significant figures because there's no decimal point at the end. So this one has two. 1 inch is 2.5 centimeters. That's exact. And 12 inches, 1 foot, is also exact. So our answer should be rounded to two significant figures. So 1, 2, after the 4 is a 1, so we just put 0.74. So that's how many feet cubed is 21,000 centimeters cubed. So that was just kind of a warm-up. Now we get to a little bit more advanced dimensional analysis problem. So here we have Bilbo Baggins. He has a kitchen. It's 15.5 feet by 8.0 feet. He hires a dwarf Beaufour to retile his kitchen floor. Beaufour charges 45.5 caster for every 2.25 meters square of floor. So how much will it cost Bilbo to get his floor retiled from using this dwarf? It should be U here, not an O. And so Bilbo Baggins' kitchen is 15.5 feet by 8 feet. The dwarf Beaufour charges 45.5 castar for every 2.25 meters squared of flooring. So we want to know how much it's going to cost Bilbo to get his floor retiled. So and again, there's many different avenues to solve this problem. If you do it a different way and we get the same answer, no problem. And it gives us the conversion factor we want to use is 1 inch is 2.54 centimeters. So what we can do first is we can take the length and the width of Bilbo's kitchen, and we can convert that to how do we want to do it? Convert it to let's start it. We take length and width in feet. Okay, we'll do that. Length times width give us feet squared. And then we can get inches squared. Again, we have to go this route because it gave us 1 inch is 2.54 centimeters. Then we can get centimeters squared and meters squared. So what we're going to do is we're going to take the length and width of Bilbo's kitchen, find the feet squared, convert that to inches squared. Then we can convert it to centimeters squared and then meters squared. And once we get meters squared, then we can convert it to how much castar it'll cost. So this is the route we're going to take. So in addition to the 1 inch is 2.54 centimeters, we need to know how many inches in the foot. And we need to know how many centimeters in a meter. And now we need to square those conversion factors, because we're dealing in squared units. Now we have all of our squared conversion units. We can go ahead and start working on solving the problem. So first I'm going to go ahead and find the area. The area equals length times width. That's going to be 15.5 times 8. So this is 124 feet cubed. So now we can do our conversion between feet squared to Castar. Again, we're starting with 124 feet squared. Now the calculator, that's an exact, I mean, not exact, but it only displays 124 on the calculator. So that's why I only wrote 124. So now we're starting with feet squared. We want to convert to inches squared. So in our conversion factor of feet squared and inches squared, we're going to put feet squared on the bottom, inch squared on top. So now we have inches squared. We've done step one. Now we're inch squared. Next, we got to do centimeters squared. So in our conversion of inch squared to centimeter squared, inch squared will go on the bottom, centimeter squared will go on top. So now we've converted to centimeters squared. The next step is meters squared. And so for a conversion factor of centimeter squared to meter squared, centimeter squared goes on the bottom, meter squared goes on the top. And lastly, we want to go from meter squared to Castar. Now this conversion factor is 4.5. Castar equals 2.25 meters squared. And so since we're starting with meters squared will go on the bottom. And Castar will go on top. So now you see everything cancels out except the unit that we want. So again, you multiply everything on top, you divide by everything on the bottom. So we get about 1.6177 cast star. Now we got to round to the correct number of significant figures. So 15.5 has 3 significant figures. 8 feet has 2. 45.5 has 3. 2.25 has 3. Now all of our conversion factors, those are exact conversion factors. So we don't have to worry about them. So we got to round to 2 significant figures. So 1, 2. The answer will be 1.6 cast star. So back to this problem, I forgot to multiply by 144, so let me do that. That's why my number was a little bit low. So you get 232.95. So we get 232.9595 cast star. And again, we have to round this to 2 significant figures because in our numbers given to us, we only have the lowest one is 2. So 1, 2 after the 3 is a 2. So the correct number should be 230 cast star. I thought that was a little bit cheap to be getting a floor retile, but yeah. So on this note, we'll pause. So when we're looking at measurements, we have to pick a certain type of measuring device to perform our measurements. So for example, here's a lucky leprechaun with a pot of gold, and he wants to use something to measure the pot of gold, the mass of the pot of gold he has. And there are many different types of measuring devices out there. So depending on which type of measuring device you use can dictate, the accuracy and precision in your measurement. So for example, for measuring mass in the lab, we have many different types of ways to measure mass. We have what's called an analytical balance. We have a top loading balance. So these are some of the balances you would see in a lab. Now, just to bear in mind that whenever you have an electronic measuring device, all of the digits displayed on it are significant. The last digit displayed is always your estimated digit. But whenever you're using an electronic device, you have to record everything displayed on the measuring device because they're all significant figures. Then we have a triple beam balance, and then of course our normal Bath scale. Now the reason I chose these is because they're all at varying degrees of precision. And so I'm going to show you how it kind of slightly changes the mass of Lucky Leprechaun's pot of gold. So for the first one, if he measures it on a analytical balance, he can measure down to the 10,000ths of a gram. Very precise measurement. With the top loading balance, he can measure down to the thousandths of a gram. So not as precisely as an analytical, but pretty well precise down to thousandths or milligram level of the scale. Now, a triple beam balance, we can measure down to the 100th of a gram, but we have a little bit more uncertainty in that measurement. And then we have a bathroom scale where we can measure to a 1/10 of a gram. And as you see, we're kind of losing precision as we go from one balance to the next. Now, to give you an idea of the uncertainty in these types of measuring devices, let's assume that 1 gram of gold is $45.66. And so if he was to take the mass from the first balance, he would get $11,444.93. If it was a top loading balance, we get $11,444.90 based on the proved significant figures. For the triple beam balance, we get $11,445. And for the bathroom scale, he would get $11,450. So depending on what you use to measure, your quantity can kind of dictate, further down the road, your precision in your measurement, and that can, determine how much money you would get. So if you used the least precise measuring device, you would actually have received $5.07 more than if you use the most precise measuring device listed here. So because there's uncertainty in the measurement, you have fewer numbers of significant figures. So now we're going to show you some examples of how to determine the number of significant figures in a measurement. And so with significant figures, we've always been saying that it's the certain digits plus one uncertain or estimated digit. And so your certain digits are based on the smallest tick mark of your measuring device. Now, typically the smallest tick mark is some power of 10. It could be the ones place, the tenths place, or even the hundredths place. And with those, it's fairly easy to determine the estimated digit. However, you do have some glassware that the smallest tick mark is not, say, when we're looking at smallest tick mark, we're saying things like 1 milliliter, 0.1 milliliters, 0.01 milliliters. These are the most common ones, but we do run into some glassware that have, instead of 0.1, it may be 0.2 milliliters, and there it becomes a little bit more ambiguous as to how to determine the estimated digit. But we're going to stick with those glassware that have a clean, power of 10, smallest tick mark, like 1 milliliter, 0.1 milliliter, or 0.01 milliliter. And so the uncertain digit is typically half the smallest increment on your measuring device. So if your smallest increment on your measuring device is 1 milliliter, then your estimated digit would be in the tenths place. If your smallest tick mark is 0.1 milliliter, then the estimated digit would be in the hundredths place. So I'll make a little chart here. So if the smallest tick mark is 1 milliliter, your estimated digit would be in the tenths place. It's always to the right of the last certain digit. If it was 0.1 milliliters, then your estimated digit would be to the hundredths place. And then if it was, you knew accurate down to the hundredth milliliter, then it would be to the thousandths. So this can give you an idea of the estimated digit based on the smallest tick mark. So you have to look at your measuring device, determine the smallest tick mark, and then you'll move one place to the right. So if it's in the ones place, you go to the 0.1 place. That's going to be your estimated digit. So now if we look at this graduated cylinder, when you pour liquid into a graduated cylinder, it forms a curved surface. You read the measurement at the minimum of the curved surface. And so from this, if we look at the close-up, we see that we know for certain that the volume of water is 40, 41, 42, 43. So our certain digits is 43. And you'll see the smallest certain digit is the ones place. So that tells us our estimated digit should be in the 0.1 or the tenths place. And so the estimated digit is an estimated digit. It's based on the observer. So I may say if it's close to 43, I may say 43.0. But if you put 43.1 or 43.2, that's still acceptable estimated digit, because at the end of the day, it's a estimated digit. So again, the smallest increment is 1 milliliter. So since the smallest tick mark is 1 milliliter, our estimated digit should be in the tenths place. Now, typically, and this is just common convention, typically when you're doing the estimated digit and it's based on, you know, a power of 10, like ones, tenths, or hundredths, typically we use either a 0 or a 5. So 0 we use if we think it's very close to that smallest certain digit, or we use a 5 if we think it's between the two smallest tick marks. And this is just common convention, but like I said, you can put what you think it is, or if you think it's 43.1, you can put 43.1, but this is just common convention. So based on that, we would say this measurement is 43.0 milliliters. And notice that it has 3 significant figures. So whether you put a 0 here or a 1 or a 2, you would still see that it has 3 significant figures with it. And so that's the key thing, is that you want to make the measurements to the correct number of significant figures. So here we have a ruler. We want to know what is the measurement of this red line. So again, with measurements, we have the certain digits plus 1 uncertain digit. And so for our certain digits, we look at the smallest tick mark on our measuring device. And you see here that the big tick marks are centimeters in the ones place. So we got 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, etc. Now between the 0 and the 1, we have 10 tick marks. So this tells you that we're measuring down to the 10th of a centimeter. So our certain digits go to the tenths place. So 0.1 centimeter, that's about as certain we can get. So our estimated digit should go to the hundredths place, because that's to the right of the last certain digit. So for our certain digits, we know for certain that it's 2. We know that for certain. We know it's 2.1, 2.2, 2.3. So our certain digits is 2.3. Now our estimated digit, and again, this is based on the observer, I'm going to put a 5. So then our measurement would be 2.35 centimeters. Now again, the estimated digit can be different. Again, 2.34, 2.33. You know, 5 would probably be the highest I would go, because it seems more if it's in the middle, or it's a little bit less than the middle. So somewhere in there, I would put an estimated digit. So again, this measurement has 3 significant figures. So here again, we have another graduated cylinder. We want to make sure that we read the volume at the minimum of the meniscus. So right about here. And so for, again, between 50 and 60, we have 10 tick marks. So each tick mark represents 1 milliliter. So our smallest certain digit is 1 milliliter. So that means that our estimated digit has to be in the tenths place. And so from this, we know for certain that it is 53 milliliters. We know that for certain. Now, since it's very close to 53, you can put 53.0 or you can put 53.1, but I wouldn't put 53.5 because it's closer to the 53 than it is between the two. So you know things like 53.0, 53.1, 53.3, etc. Those would be acceptable values. So here we have 53.0 milliliters is the volume of the graduated cylinder. And so this again has 3 significant figures. And you always read at the minimum of the meniscus. Now another important piece of glassware that we use a lot in the lab is a burette. And the interesting thing about a burette is that you always read it from the top to the bottom. So in the graduated cylinder, you read it from bottom to top, but for a burette, you always read from top to bottom. And so you'll notice here that for a burette, this is 10, this is 11. Between the two, we have 10 tick marks. So our certain digit or digits go to the tenths place. So therefore, estimated digit goes to the hundredths place. So again, if you count between 10 and 11, you count 10 tick marks. That means the smallest certain digit is 0.1. Therefore, our estimated digit is 0.01. So again, our certain digits, we know for certain it's 10, 10.1, 10.2. And again, you always read at the minimum of the meniscus. So this is our certain digit. Now for our estimated digit, since it's between 0.2 and 0.3, I'm just going to put a 5. And so our measurement be 10.25 milliliters. Now, one thing to bear in mind is when you get to smaller and smaller, more precise glassware, it becomes harder and harder to distinguish the estimated digit. Because some may make the argument that when it's between 0.2 and 0.3, you should just put a 5 for the estimated digit because it's hard to distinguish between 0.05 and 0.06 milliliters, for example, or 0.05 and 0.04 milliliters as well. So they're saying as it gets smaller, the ability to discern between the two becomes a little bit harder. So that's why they're saying if it's between the two, just put a 5. If it's close to one of the smallest tick marks, you put a 0. That's the common convention when we take measurements.